Okay, this is the first lesson and this is based on physical quantities and units. And what do we have here? This is the specification from OCR. So, explain that some physical units consist of a numerical magnitude and a unit. That's nice and straightforward. Magnitude, we just have a number. So here's a number, here's 22. Has it got a unit? Not at the moment it doesn't, so that's not going to make much sense. So what are we talking about? 22 volts? Are we talking 22 meters? Are we talking 22 amps? Okay, you've got to make sure you've got the units and a magnitude. There are exceptions, obviously. If we've got a ratio, that's not going to have a unit, but pretty much everything that you cover will have a unit. If you don't put the unit, you're going to lose marks. Okay, next part in this lesson is use correctly named units listed in the specification. Okay, there are 6 base units and 6 base units only. Let's go through them. The first one is the meter. Okay, a little bit of a French spelling there. That's a meter that you measure something with. That's the meter. Okay, we don't want a meter to measure something. We want the meter. Okay, that is going to be for length. And that is a small m. Not a great big M, because that's going to be for mega. Okay, so we want a little m. Next one is the kilogram. This is a little bit of an exception because we use kilograms. It's not grams. Don't use that. All of them are units like this, but the kilogram is got to be kilogram as a base unit. So all your calculations must be in kilogram. Okay, the next base unit is the second. Okay, that's a little s. Nice and straightforward. The ampere. Another French word. Can't remember the man's first name, but his name was Mr. Ampere. Okay, you may have known him because we say amps. Okay, that's going to be okay. If you say amps or amp, that's fine. But strictly speaking, an ampere, and I'll stop using the silly French accent, that is a capital A, and that's to measure electrical current. We can just fit that in there. Right, the next one, if you've done triple science, you will be familiar with the Kelvin. This is the absolute scale of temperature, and it is a little K. So this is temperature. Okay, 0K being absolute 0, 273K. That's about 0 degrees C in Celsius. No idea what it is in Fahrenheit because only the crazy Americans use Fahrenheit, so we're not going to be bothering with that. Okay, so there'll be lots of calculations where you need the temperature, and there's some where you've got to turn it into Kelvin. But don't forget the base unit is the Kelvin. Okay, next. One you've probably not come across before, and you're not going to have much dealings with it, and that's candela. Surprise, surprise, something to do with light. And this is luminosity, or luminous intensity. Okay. Last one, it's the mole. Okay, not a little creature with a little funny little nose and little ears like that and little eyes that digs holes in the ground. Okay, it's not that type of mole. It's the mole. It's the amount of a substance. So, if you're doing chemistry, you're going to know all about the mole. Okay, the symbol is MOL. That's supposed to be one of my L's. Okay, you won't actually come across that until A2 in physics. Okay, but those units are all of the base units, and from those 7, all other units can be derived. All others. Okay, I'm going to give you an example. So, Clever Clogs at the back says, what about the newtons, sir? That's the base unit, isn't it? N. And I go, no, it's not a base unit. It's not, because what do we know? It's made up of base units. Force, well, that is newtons, but we know it's mass times acceleration. I've run out of space, I'll just do ACC. Okay, so what is mass? Mass is in, don't forget the kilograms times acceleration. Acceleration is meters per second squared, or I'll write this a slightly different way. Kilograms per meter over second squared, like that. I suppose I could write it like this as well, couldn't I? S to the minus 2. Okay, I won't do that, don't worry about that. Okay, we'll complicate things later. Okay, so this, we don't say the Newton in base units, we use these units here. Okay, so now we'll complicate it. Kilograms, meters, S to the minus 2. That's all the same thing. Okay, that is the Newton expressed in base units. Okay, what does the spec say? It says, correctly use the following prefixes and their symbols to indicate decimal submultiples or multiples of units. So what do we do when we've got really big numbers and really small numbers? Okay, let's go through what we have. Okay, let's start at the top. If you've got a really big number, we are going to use peta or peta, depending on what part of the country you come from. That is 10 to the 15. Okay, the symbol is a capital P. Tera. Some of you are going, oh, I've heard of tera, because that's terabytes in computer talk. Okay, lots of bits of information. That's a capital T. Okay, so if you had terabytes, you'd probably go terabytes like that, wouldn't you? Yeah. Or if you had terameters, teravolts, that would be a bit dangerous, wouldn't it? Teravolts. Okay, let's take that out of the way. Back to what we were talking about. Tera. Okay, giga. Okay, everybody's heard of giga. Not gaga, giga. Okay, notice how these are going down in 3s. It's all very convenient. Giga, capital G, nice and straightforward. Mega, megapixel camera. Yes, that's all about big numbers. Okay, 10 to the 6, again going down by 3. Okay, what should we go for next? Oh, we've got mega. Okay, capital M, kilo. Okay, that is a K. That's 10 to the 3. That's the one you're probably most familiar with. Kilometers. That means 1,000 meters. 10 to the 3 is that, isn't it? Yeah. So that's how it's done. Take that out. What have we got next? Okay, we're not going to go down by 3 now. We've got a kind of intermediate one that we tend to use, and that's centi, little c. Unfortunately, that's used also for the speed of light, but hey-ho. That's 10 to the 2. That's basically common usage because centimetres is such a useful unit to use in normal everyday life. In the same way in the old system, the old imperial system, people used inches. Okay, because that was a kind of useful measure to use. Yeah, that's 25.4 centimetres in an inch. You don't need to know that. I just thought I'd tell you that. It gives me something to talk about while I'm rubbing that out. Okay, so centi. Now let's go the other way. What happens when we have really small? Okay, so we're going to go milli. And you go, I've heard of that, sir. I've heard of millimetres. That is 10 to the minus 3. Whoops, so you've heard of that before. So somebody says, oh, that's 1 millimetre. Okay, so that's 0.001 of a metre. I'll put a 0 there so you can see where my decimal place is. So that is the same thing. Okay, instead of writing all these nonsense zeros, getting lost, we don't do that. So I don't want to see that in your exam questions or your notes, lots of zeros, use these scientific notation. Micro. Okay, 10 to the minus, have a guess. Yep, you got it, -6 micro. And that is this lovely Greek symbol, which I'll draw a big one here. It's kind of a funny U like this. If you're writing it, I'd write it exaggerated. If you look on the script on a computer, it's a little bit more reserved in its style, but make it fairly obvious if you're writing micrometers so the examiner knows what you're talking about. Okay, micrometers to the -6. Nano, everybody's talking about nanotechnology, -9. Okay, nano, little n. Okay, something that's really small, wavelength of light. Okay, that's in the hundreds of nanometers, so you could have 450 nanometers. Okay, that's the wavelength of visible, well, one of the colours of visible light. And nanometers, okay, 10 to the -9. So what if you want to go even smaller? Pico, 10 to the minus, you're going to guess? Yes, it's -12. Little b. And femto, when you use capacitors and capacitance, you're going to have to use these numbers, the femto and F, because you're not going to be writing this in your exam paper, all of this nonsense, because that's just plain silly and you'll make mistakes, okay? So this is the expectation, this is the scientific notation you're going to use. Okay, why is the crazy man put a photograph of his calculator here? Little trick that lots of pupils don't use, don't realise they've got it. If you get an answer and you've got something like this on your calculator, if you use this eng button, it will move the significant figure, no it won't, it'll move the decimal point 3 along and change your times 10 indicator here. So as it moves this one, this way, it'll move this the other way. So have a little play with that. And if you do inverse, or shift, yes, shift, isn't it? It'll work the other way. So if that goes up, that one will go down. So have a little play with that. The integrity of the number stays the same, okay? But it's just quite useful. Maybe if you want an answer, let's say you wanted an answer in nanometers, so you wanted the answer in -9 because the exam says or indicates that it wants it in nanometers. You can shuffle it one way or shuffle it the other way to get the final answer to -9, and it then will adjust the decimal point on the display there. So the integrity of that remains the same while you press eng or shift eng. Okay, you'll have to play with that yourself to see what I'm randomly going on about. Okay, scalars and vectors. What does vector mean? Vector means it just has a direction. So let's just do a big list. We'll have scalars here, vectors there. So scalars don't have a direction. Mass, does that have a direction? Of course it doesn't. Okay. Distance. You're probably thinking, well, that's a bit odd. Well, surely that has a direction. Nope, because its displacement is the vector version of distance with a direction, if that makes sense. Okay, so get that in your head. Displacement is a vector. Distance is a scalar. Okay, energy, does that have a direction? Nope. Okay, speed. That's the one that doesn't. And velocity is your vector. It has a direction. Volume. Does this bottle of Coke have a direction? No, it doesn't. Neither does temperature. Temperature. Okay, momentum is here. For those who remember GCSE, mass times velocity is momentum, so obviously if you've got a direction there, you're kind of stuck with the fact that that's got to be a vector as well. Forces, do they have a direction? Of course they do. They're a great big sodding arrow, aren't they? So that's got to be a vector. Let's take that out to leave that nice and tidy. Okay, so we've got one missing. I'm going to put it up here. That's acceleration, because that's the change in velocity. Acceleration. Can't talk and write at the same time. That's a little bit sad, isn't it? So 1, 2, 3, 4, 5. And we've got 1, 2, 3, 4, 5, 6 written down there. That sounds good. So you've got to remember scalars and vectors.